Good afternoon, ladies and gentlemen. I'm glad to see you all here in the conference room at the Expo 2020 in Dubai. And I feel the energy of everyone who is joining online via YouTube and Facebook, including my colleagues. I hope it's not too cold in Moscow now. So greetings to all the guys there. My name is Borislav Nesic, and I'm a senior specialist in 12 Fuel company. I work in the department for marketing of nuclear fuel cycle and for international relations. I've been working at 12 for more than 10 years. And throughout these years, besides my main duties, it's been my privilege to accompany several international delegations to different nuclear fuel cycle facilities. Today, it is my pleasure to welcome you all to the virtual nuclear fuel cycle facility tour. So this is a tour to machinery manufacturing plant. So machinery manufacturing plant, do you have any ideas? So what does it deal with? So is it about equipment or is it about machinery? Yeah, manufacturing something. Do you remember the tour of floating plant, nuclear floating plant? Yes. And do you remember that the great speaker, he presented like some tube, some assembly which were supposed to be inserted in the reactor? So basically, it's the main business of MSZ. So this is the shorthand form for machine manufacturing plant. It is one of the largest nuclear fuel fabricators in the world. So MSZ was established more than 100 years ago in 1917. So it is more than 100 years old. And first, its business was production of munition items for army purposes, but back in 1955, it was converted to the nuclear fuel fabricator. I hope you're going to enjoy the tour, and I'll run through today's program. So the tour will take about 40 minutes, but of course it will depend on the questions that you can ask here, that you can ask during online translation. It's up to you. And so first you will see the introduction of the plant. So it's going to be a presentation. Then you will be taken to 3 major facilities of MSZ plant. So they are fuel pellet manufacturing, fuel rods and fuel assemblies manufacturing, and the final stop will be at fuel components manufacturing facility. We'll have 2 Q&A sessions in this tour. I'll try my best to answer most of the questions that you ask. In case I will need some extra consultations with our technical experts, I will get back to you via email when I'm back in Moscow. So let's the tour to start. MSZ is part of Rosatom, and Rosatom, as you know, is the global leader in the nuclear industry. So we provide high-demanded solutions for power engineering sector. Today, the order portfolio of Rosatom is more than 130 billion US dollars, and there are 35 reactor units in the international portfolio of Rosatom. So we provide services and products to more than 50 countries in the world. So Rosatom covers all nuclear fuel life cycle, not only nuclear fuel, so the general nuclear life cycle, starting from mining, including nuclear power plant constructions, maintenance, operation, back-end solutions, as well as decommissioning of nuclear hazardous facilities. So, and Rosatom's fuel division 12 covers most part of front end of nuclear fuel cycle. So, well, it doesn't mine, but it covers conversion, enrichment, and of course, fabrication. So, Fuel Company 12 was established in 1996 to unite under the one management company all of the conversion, enrichment, and fabrication plants that existed in Russia. And throughout these years, we are trying to perform our best to improve our products, to come up with new solutions for a nuclear fuel cycle market. Besides front-end services and production, there are also enterprises which produce gas centrifuges. They are also under TWEL's management. So today, TWEL supplies nuclear fuel to more than 70 nuclear power units all over the world. And so it makes 70% of the global market. We also provide fuel to research reactors in more than 10 countries of the world. So basically, we're the global leader, and MSZ is one of our nuclear fuel fabrication facilities. So besides nuclear solutions, TWEL also provides non-nuclear services in metallurgy and 3D printing, not nuclear, but just energy storage facilities, as well as other solutions in chemistry. So as I told you before, MSZ was established in 1917, and first its activities were dedicated to munition production. In 1945, MSZ became the first industrial plant that was included in the Soviet atomic energy project. In 1954, MSZ produced fuel assemblies for the very first nuclear power reactor in the world. So do you know where this reactor was located? So the very first nuclear power reactor? So it was in Russia, in the Soviet Union, in the city of Obninsk. So Obninsk was the very first nuclear power plant that existed in the world. And MSZ was the supplier of fuel to this plant. So as I also told you, in 1996, MSZ was included in the fuel company as well. And in 2017, it celebrated its centenary. So it's also interesting to mention that besides supplying fuel to nuclear power reactors, MSZ also produces and supplies fuel to not only floating nuclear power reactor, but also to the nuclear fleet of icebreakers. And the very first icebreaker, Lenin, was launched back in the Soviet Union. Besides production, there are also a lot of other competencies involved in MSZ plant. So there is the testing and R&D laboratories. There are different engineering centers that manufacture and provide equipment, high-end equipment needed for the production of nuclear fuel. And the main product of it, nuclear fuel pellets, fuel rods, and fuel assemblies, of course, fuel components. So I'm not going to get into too much details about these products, because after my presentation, you're going to see the videos, you're going to visit the facilities where all these products are manufactured. And if we speak about production scope, so mainly MSZ produces nuclear fuel. So it fabricates nuclear fuel for reactors of Russian design. Their channel reactors are BMKs. There are also VVR reactors of 440, 1000, 1200. Of course, there are also production of nuclear for fast breeder reactors, BN600, BN800. And it's interesting that MSZ also cooperates with one of our main competitors. We are cooperating with Framatome for more than 20 years. And in this cooperation, MSZ produces fuel for BWR and PWR reactors. So for light water reactors of foreign design under cooperation with Framatome. And speaking about the scope, the fuel assemblies which MSZ produce, I want to go back to that slide which you have already seen, and to mention that there is another nuclear fuel fabrication plant located in Russia, also in the fuel company TWEL's structure. So this plant is located in Novosibirsk, and it's also a nuclear fuel fabrication plant. And besides fuel for Russian design reactors, in Novosibirsk we have developed the TVSK fuel. So this is Russian developed fuel for PWR reactors of foreign design. So all of the best solutions for VVR reactors were implemented, integrated in this TVSK solution. And we have already had a successful ATA program of this TVSK fuel abroad in the commercial reactor, and very soon we expect to start commercial supplies to our customers abroad. One other interesting thing, so as I told you, besides fabrication facilities, we also have enrichment and conversion facilities. And one of these plants located in Seversk, historically, Seversk plant was dedicated to conversion and enrichment. But nowadays, we can call it another fabrication facility of Rosatom, or fuel company as well. Because the remixed fuel, so the brand new uranium plutonium fuel, is manufactured in Seversk. So there has already been like lead test rod program performed in Russia, and last year we launched the first LTA program of remix of uranium plutonium fuel. So the interesting aspect of this fuel is that the fuel could be recycled multiple times. And this brings us to sustainability, to the sustainable nuclear fuel cycle. Besides remix fuel, we also have a first closing nuclear fuel cycle project, which is implemented also in Seversk. So this is called breast reactor, and it's also the brand new project that brings us closer to close the nuclear fuel cycle, because on the one facility, we are integrating the fast breeder reactors with the use of lead coolant, as well as fabrication facility of mixed nitride uranium plutonium fuel. After this project comes to life, when it becomes successful, so the world will come closer to close the nuclear fuel cycle, which will make nuclear even greener and even more sustainable. Of course, coming back to MSZ, considering all the competition in the world of nuclear fuel cycle, it is very important to provide the top quality products. So that's why MSZ has been certified by different international organizations in terms of its product quality or ecological compatibility and other things. So you can see a lot of different certificates on this slide. Go too deep into the details. And as part of Rosatom, as part of TWEL, MSZ, TWEL, Rosatom, we can provide integrated offer to the world nuclear industry customers. So because under Rosatom, we have all the possible enterprises that cover the whole nuclear life cycle. So as I said, it's not only nuclear fuel, it's production of different equipment. It's also the construction of nuclear power plant, it's backend solution, decommissioning solution. So Rosatom can also offer the nuclear fuel infrastructure development if we speak about the newcomers in the nuclear industry. Speaking about MSZ, as well as about all other enterprises in the structure of TWEL and Rosatom, we offer a lot of important projects for the public welfare. So that's why MSZ contributes to educational development of all their citizens in this city, in the city of Elektrostali, where MSZ plant is located. And we have a lot of different social projects important for public welfare. And of course, MSZ, TWEL, Rosatom, as part of nuclear industry, we contribute to sustainable development goals. Because Sustainable Development Goals of United Nations, they suppose that the clean and affordable energy is brought to the world, and that's what nuclear industry can do. So to provide the clean and affordable energy so that we can ensure the economic and industrial growth of the city, of the country which goes to nuclear. So this brings me to the end of the overall presentation of MSZ in the structure of Rosatom and TWEL. But now you're going to see the most interesting part, because you're going to visit the facilities where all the magic is taking place. If you have any questions now, by the way, you can ask them related to the presentation. If no, you can ask questions after visiting the shops. So let's start.
We are in the fuel pellet manufacturing facility. This shop manufactures fuel. We are in the fuel pellet manufacturing facility. This shop manufactures fuel pellets for various types of nuclear reactors of Russian and foreign designs. Fuel pellets are manufactured using uranium dioxide powder fabricated from uranium hexafluoride. Uranium hexafluoride has a particular property which is very important for the applied flow process. Its specific feature is, as far as the flow process is concerned, that it can easily transform from solid to gaseous state. For transporting purposes, UF6 is placed in special leak-tight cylinders, and when it is put in production, it is transformed into gaseous form in order to be converted into another substance, uranium dioxide, in a special reactor. This operation is called conversion. Prior to pressing, uranium dioxide powder is mixed with certain process additives, then processed in a special equipment to compact the mixture, and spheroidized together with a dry lubricant to obtain homogenized and fluid compact powder. Special compact powder preparation equipment is used for this purpose. Dynamix mixer prepares the mixture made of uranium dioxide and process additives. Compact powder preparation equipment consists of a hammer mill, a roller unit, a granulator, and serves the purpose of changing powder particles' shape and providing these particles manufacturability, fluidity, and bulk density required for fuel pellets pressing at high speed. Uranium fuel pellet is shaped as a cylinder. The prepared mixture is pressed so that the compact powder would get the required geometric shape. Compact powder is pressed in automated mode by means of presses and carefully loaded into molybdenum boats using a special soft boat loading device. After that, the pressed fuel pellets are transported by a conveyor into the sintering furnace. Sintering is a process that takes a long time to complete. It can go on for 1 to 3 days, depending on the fuel pellet type. While the fuel pellets are inside the furnace, they pass through a number of temperature zones, where a fuel pellet pressed from densely compacted powder obtained its ceramic structure. To achieve the required dimensions, a sintered ceramic fuel pellet is ground in automated mode in a grinding machine, and then it undergoes automated sorting by diameter and visual appearance. After grinding, acceptable fuel pellets are loaded onto special trays in even rows of the same length. Each operation is subjected to production and quality control. Acceptance inspection takes place in the course of batch manufacture, and an applicable certificate is issued based on its results. After submitting the product to the customer's representative, it is sent to fuel rod and fuel assembly manufacturing facility. All the scrap and production waste removed in the course of production control is processed and put back in manufacture as the aforementioned process additives.
So has anybody been present here during the Novovoronezh nuclear power plant tour? So I think you remember that the speaker brought the fuel pellet here, so you could see how small it is, but how much energy it provides. So that was the visit to the fuel pellet manufacturing facility. Now we're going to the next stop. This will be dedicated to fuel rod and fuel assemblies manufacturing. So let's see the video.
We are at the VVR-1000 fuel rod and fuel assembly production site, where we manufacture fuel rods that subsequently will be used in fuel assembly manufacture for VVR-1000 or VVR-1200 reactors. A fuel assembly is a 5-meter-long hexagonal assembly. Mass of one fuel assembly exceeds 700 kg. Subassembly located in a fuel assembly's upper part is called the headpiece. When handling an assembly, it is gripped by its headpiece. The force required for a fuel assembly's compression in the reactor core is ensured by its headpiece. Subassembly located in a fuel assembly's lower part is called the tailpiece. It guides the coolant flow into the fuel assembly. A fuel assembly is installed and fixed in place in the reactor core by means of its tailpiece. Within a fuel assembly, between its headpiece and tailpiece, there is a fuel bundle comprised of fuel rods. A fuel rod consists of a thin-walled, long zirconium cladding tube with the end plugs welded at both ends. UO2 or UO2 plus gadolinium-203 fuel pellets are loaded inside the cladding tube. One fuel assembly may operate in a reactor for over 5 years. If we are talking about the manufacturing process, then place for storing cladding tubes, fuel pellets and applicable components, end plugs, compression springs, etc. are organized at the start of the manufacturing line. Prior to putting cladding tubes into manufacture, they are checked on the gauge plate for straightness, visual appearance and length, after which an applicable traveler is generated. The next step is to blow out the cladding tubes and dry them, which is followed by welding of the first weld, where low-end plugs are welded to cladding tubes. After that, cladding tubes are weighed and loaded with UO2 fuel pellets. Then the second weighing of loaded fuel rods is performed, and based on the difference of the measured masses, the fuel stack mass is determined. Subsequently, compression springs are inserted into the fuel rod. These springs are fixing and compressing the fuel stacks loaded inside the cladding tubes to eliminate gaps between fuel pellets. This is followed by the dusting operation, when any accumulated dust are evacuated from loaded fuel rods by vacuum suction, and afterwards these fuel rods are preliminarily pressurized with helium gas. Then welding of the second weld is performed, where the fuel rod's inner volume is filled with helium under the specified pressure, and the upper end plug is welded to the open end of the cladding tube. High pressure of helium inside fuel rods is required to ensure that when operated, they do not crumple under the excess operating pressure occurring in the reactor. Fuel rod manufacturing steps end after welding of upper end plugs, and fuel rod inspection steps start. They are carried out using special inspection equipment. The following is inspected: fuel rod length, helium pressure under cladding by non-destructive testing, fuel rod leak test, fuel stack inspection where the following parameters are checked: the availability of compression spring, gaps or chips between the pellets within the fuel stack, as well as deviation in uranium-235 content in single fuel pellets and the average for a particular fuel rod, weld length, uranium contamination of fuel rod surfaces. After that, fuel rods are brought for acceptance inspection, performed by quality control inspectors, who check fuel rod straightness, their visual appearance, dimensions, alignment diameters at their lobel diameter reduction locations, and surface cleanliness. After QC inspection, fuel rods are assigned the status of accepted products. They are certified by lots and loaded into the containers intended for storing fuel rods between operations. To be able to load fuel rods into a reactor, they must be assembled into a fuel assembly. The primary component providing rigidity to a fuel assembly is its skeleton. Spacer grid is an equilateral hexagon of a honeycomb shape. It consists of 312 cells hooked by an outer strip, and fuel rods are inserted into these cells. Spacer grids ensure that the inserted fuel rods are properly fixed inside the assembly relative to each other. Prior to inserting a fuel rod into the applicable skeleton, its surface is covered by a protective lacquer coating, using a special lacquer coating equipment to prevent cladding damage. Fuel rods are inserted in the cells of the skeleton spacer grids at the assembly bench, thus assembling the fuel bundle in accordance with the loading pattern. Special adapters are put on the fuel rod end plugs. Those ensure fuel rod alignment during assembling. Prior to inserting a fuel rod into a skeleton, water glycerin lubricant is introduced onto fuel rod surfaces to reduce the force of fuel rod movement through the spacer grids. After passing through all the spacer grids, adapters are removed from the fuel rod end plugs, and fuel rods are moved further forward until they come in contact with the support grid. Once the bundle is assembled, it is transferred into vertical position and sent for washing operation, where the lacquer coating and the remaining traces of water glycerin lubricant are washed off. Washing is performed in hot distilled water. After that, the fuel bundle is dried and its visual appearance as well as dimensions are inspected. Then the fuel bundle is moved to the bench where its head and tail pieces are mounted thereon. Fuel assembly is finished after installing its headpiece and tailpiece, and it is sent for acceptance inspection. In acceptance inspection, the following is checked: fuel assembly dimensions, length and weight, as well as the forces of absorber rod movement inside the guide tubes. After that, the fuel assembly is checked by putting it inside the jig, simulating a reactor core cell, and then sent for packing operation. Prior to packing, it is checked that guide tubes and the central tube are free from foreign materials. Inspection is performed in 2 steps, by means of a special device and using a video endoscope. Following that, the final packing takes place. The fuel assembly is loaded into a transport package. Depending on the delivery option, fuel assemblies may be transported together with or without rod cluster control assemblies. Subsequently, markings are introduced on transport packages, and applicable fuel assembly documents are issued.
So that was the tour to the fuel rod and fuel assemblies facilities. And I can tell you that a lot of foreign delegations were really impressed with the level of automatization of the production in MSZ. It even includes some nuclear fabricators who are also having a tour through the facility of MSZ, and everyone expressed one and the same opinion that the level of automatization at MSZ is at the really, really high level. And I can tell you that we are working to improve it, like to make it even more automated in the future. So you could also mention during the visit to facility of fuel assembly and fuel rod manufacturing that it's not only fuel rods that make fuel assembly, there are a lot of other components to make it. So our final stop will be at the nuclear fuel components manufacturing shop. So let's see.
We are in components manufacturing facility. This shop manufactures fuel rod and fuel assembly components for VVR 440, VVR 1000, RBMK 1000, BN 600, BN 800, CEFR and more reactors. This shop concentrates primarily metal working equipment related to turning and milling, both general purpose as well as computer numerical control machines, machines for spot resistance, argon arc and electron beam welding, precision material cutting equipment, laser machines as well as water jet cutting machine, equipment for product heat treatment, electrochemical polishing, degreasing, as well as acid and caustic treatment, spring coiling machines, and a whole lot of other equipment items. Stainless steels and their alloys, zirconium, aluminium, graphite, and other materials are used as input materials in this shop. The shop includes several sites. It all begins in the pre-production provision site, where the input materials are received and cut in accordance with the applicable drawing requirements. If needed, input material can be heat-treated. They can undergo hammering, smithing, and shot blasting. Markings can be introduced on them, and input materials can be prepared in order to be sent to the core production site. As an example, let's examine the manufacturing process related to spacer grid production. We will start from the cutting operation. Input tubes are cut into cell work pieces. Metal, in this case a thin-walled tube with wall thickness of 0.25 mm, is supplied for cutting directly to the CNC turning machine. In the course of cutting operation, operator periodically checks the cut cell dimensions according to the applicable drawing after a specified number of cut items. Acceptable cell items are sent for degreasing in order to remove residual oil left from the cutting operation. Degreasing is performed inside the special automated washing stations that completely remove lubricant from cell surfaces. After that, cell undergoes punching operation, carried out at the automated presses, where cell workpieces, in accordance with the applicable drawing requirements, are given a complex shape by means of special punches. In the course of punching operation, the output cell items are mandatorily controlled by means of the measuring instrument specified in the flow process. After completing the punching operation, punched cell items undergo mandatory degreasing because subsequently these items will be welded together by spot resistance welding to make spacer grids. A spacer grid is comprised of several parts depending on reactor type, namely inner cell, outer cell, sleeve, and strips. Prior to welding, a spacer grid is assembled inside a special fixture that ensures proper positioning of the cells, their tight fitting to each other, which is very important to the welding process. The fixture is placed in position inside the welding machine, and the grid array is welded by means of 3 pairs of electrodes. After every 5 welded grids, a weld sample is taken to verify the performed welding quality.
So that brought us to the end of the tour. Do you have any questions now? I hope that's because it was self-explanatory. Does anyone have access to the online broadcasts? So maybe there are some questions there, no? Do you know? Great. So as I told you, by the way, you can ask questions in the comments later. So I'll check the website and I'll provide you with answers, or you can send it to my email, so if you want. Basically, I want to thank you all for being here, for watching the tour. This was the very first virtual tour of the nuclear fuel cycle facility in Russia. And this is the first in the series of tour which TVEL and Rosatom are preparing. So there is going to be the tour to another nuclear fuel fabrication facility. There's going to be a tour to conversion and even enrichment facility in the future. And I hope that we will improve and you will enjoy it even more. Special thanks to MSZ team who made this tour possible, who made all the videos, who work on explaining all the facts about the nuclear fuel fabrication. And of course, I want to thank the Rosatom and TVEL team who made this tour available for everyone. And I hope that this tour and the other tours of nuclear fuel cycle facilities will be enjoyed by everyone in the world. So thank you very much and hope to see you soon.